In the course notes, we've discussed the stability of a stable fixed point. We've derived a theorem that will tell you when that fixed point is stable. Now the question is, can you do something similar for an unstable fixed point, for a source? So pause the video, follow the same line of reasoning to prove the stability theorem in that case. To start off with, let us briefly remind ourselves of the definition of an unstable fixed point. Well, for an unstable fixed point, there should be some small neighborhood around that fixed point, some sort of epsilon neighborhood around P. So that should exist. So that might be a small number, but that doesn't really matter, such that all of the initial conditions that are inside that small region around our fixed point P will eventually map outside of that epsilon neighborhood, meaning that there should exist some sort of number k. If we apply the map k times to our initial condition, we will eventually move outside of our epsilon neighborhood around P. There's one small caveat, of course, is that this is not true for the fixed point P itself, because this will stay forever where it is, right? That's the very definition of a fixed point. And then we've said that, okay, if you look at the derivative of the map at the fixed point, and if that is in magnitude bigger than 1, then you have an unstable fixed point. Then the question is now, can we show that that is true? Now that derivative is actually going to be the limit of x going to P, by definition of the derivative, right? So that's f of x minus f of P divided by x minus P. And this derivative should be bigger than 1. And the question is, if that's the case, do we have an unstable fixed point? So this is actually a real number. This is also a real number. And the nice thing about real numbers is that you will always be in a situation to squeeze in an extra real number in between two other real numbers. So there is some sort of number a that's lying in between these two values. Let's now have a look at the stuff of which we take the limit here. Now we can consider this to be a function of x, and we're going to assume that since our map f of x is nicely well behaved, then obviously also this is a nicely well behaved continuous function g of x. So let's plot that function g of x, or at least try to imagine what it could look like. So on the horizontal axis, we have x, and then here we have g of x. We are interested in what happens at the fixed point P. And we do know that when we plug in x equal to P in our function g of x, that we will end up at the magnitude of the derivative in absolute value. So we know our function g of x goes through this point. And it's continuous. So that's the only thing we know. So we can imagine, for example, that this function, I don't know, looks like this, something like this. The exact form doesn't really matter. Only important part is that it goes through this point and is nicely continuous. Let's bring in some other players inside in this diagram here. So we have the value of 1, which is important. And then we also have the value of a, which is important and which is lying somewhere between f prime of p in magnitude and 1. So here in this diagram, you can clearly see that as soon as you stay very close to our point p, you will always be in a situation where our function here will be lying above that line indicating the value of a. So in this particular case, that's as soon as we are bigger than this point here. So if this is p minus epsilon, and then there will be another symmetric point on the other side, p plus epsilon. So for this particular function, for this particular drawing, as soon as we are inside this interval here, then we have a situation that our function g of x is lying nicely above the line represented by a here. And that's going to be relevant for our proof now, because what do we have? We have that our function g of x Let us remind ourselves again what that function was. It's f of x minus f of p magnitude divided by x minus p. So that's going to be bigger than a for all possible values x that you can think of that are lying inside that particular epsilon neighborhood that we've graphically defined here in this way. And now that's very important because we can bring this thing to the right-hand side and we can conclude that f of x minus f of p, and here it's good to remind ourselves that p is a fixed point, so f of p is actually equal to p. F of x minus f of p is bigger than ax minus p. And this is interesting because it tells us something about what happens to a point x after you apply the map. Does it move closer to p or does it move further away from p? Because what we have here, the absolute value of x minus p, that's the initial distance between x and p. So if we have p here and we start with an initial condition x over there, so this distance here is that thing over there. And then if we apply our map to x, we end up with f of x. And then this thing on the left-hand side tells us the distance between f of x and p. And this number here is a number which is bigger than 1. So this basically means that this distance here on the left-hand side has increased. So you start with a certain distance away from p, and if you apply the map, then you will have moved further away from p because a is a number bigger than 1. At this point, there's two things that can happen. Either you have already moved outside of that epsilon neighborhood, and then you're done, because that's the definition of an unstable fixed point. Or you're still inside that epsilon neighborhood, but then you can keep on playing that game again. In this formula here, you just simply replace x by f of x, and then you will keep on moving further and further out. So remember, a is a constant, so every time you apply the map, you will move further and further away with a given scaling factor. So it's basically exponential growth of the distance to our fixed point p. So there has to be some point where you leave that epsilon neighborhood. So that's indeed the proof that as soon as the magnitude of the derivative is bigger than 1, you will keep running away from your fixed point. You might be a little bit paranoid and thinking that perhaps it might be possible that, okay, once you're outside of the epsilon neighborhood, then this formula no longer applies. And then perhaps your function might do some strange things and throw you back inside the epsilon neighborhood. It's very unlikely that that would happen, but suppose it does happen, then again, the formula will kick in and the fixed point will push the orbit again outside of that epsilon neighborhood. So even in that pathological case, you will again move outside of the epsilon neighborhood. So that completes the proof of the stability criterion for an unstable fixed point.